a local potential is strong enough by the time it reaches the axon hillock, it will trigger what's called an action potential. Here's how it works. At the axon hillock of each neuron, there is a high concentration of voltage-gated sodium channels and voltage-gated potassium channels. Voltage-gated means that what opens the channel is a change in the membrane potential. Each voltage-gated channel has a particular membrane potential that will cause it to open. So, sodium starts arriving at the axon hillock, coming from the local potential, diffusing away from the ligand-gated sodium channels that allowed the sodium in the local potential. And if enough sodium, if enough positive charge makes it into the axon hillock or the trigger zone, it will reach the membrane potential that opens the voltage-gated sodium channels. This is called the threshold. We have to reach a certain level before it will turn on or open, not turn on, the voltage-gated sodium channels. Now, sodium is, as always, more concentrated on the outside of the cell. Therefore, when these channels open, sodium comes rushing in, making the cell even more positive. That's, again, depolarization, but very rapid depolarization, because once sodium comes in this channel, this voltage-gated sodium channel, it makes the membrane potential more positive, which opens this channel, and sodium comes in and it causes the next channel to open, and more sodium comes in and it becomes more positive, and the next sodium channel opens, and so a whole bunch of them open all at the same time. It just spreads and becomes this big movement or flux of sodium into the cell. And if you look at what you would see if you put an electrode in the axon hillock, here we're at the resting membrane potential. In step 1, the cell or the membrane potential here is becoming slowly more positive as sodium starts arriving from that local potential. And if it reaches this dotted line, which is the threshold or the membrane potential that opens the voltage-gated sodium channels, then they will open and there will be rapid depolarization. Now, paired with the voltage-gated sodium channels are voltage-gated potassium channels, and those open when the membrane potential reaches this high level of depolarization. Potassium's more concentrated inside the cell, so it leaves through the potassium channels. We lose positive charges, and therefore the cell becomes more negative. This is called repolarization because we are returning to the normal polarized state. You might notice that the repolarization actually goes down below where the resting membrane potential is. This is called hyperpolarization. It means that it's even more negative than normal. And the reason that it's like this is because the potassium leaves the cell so rapidly that it actually overshoots a little bit too much leaves, and we end up with a hyperpolarization. This is important because when a cell, or when part of the cell, part of the membrane, is hyperpolarized, it's harder for a local potential to push that up to reach the threshold. So we say that the part of the membrane that is hyperpolarized is refractory or resting before it can have another action potential. All right, going back to the axon hillock, we've had this action potential. The action potential is steps 2 and 3. Step 1 here is the local potential arriving. But we've had the action potential begin in the axon hillock, and these channels, these voltage-gated channels, continue all the way along the axon until the terminus. So when sodium comes in through this channel and makes the membrane more positive, that opens this channel, sodium comes in, makes it more positive, that opens this channel, sodium comes in, sodium comes in, sodium comes in, all the way down the axon, with each channel opening up the channels next to it. If you've ever seen at a major sporting event or been at a major sporting event where people start a wave, where one person stands up and then the next person stands up and the next, that's very much how you could visualize the action potential traveling along the axon. Just behind the wave of depolarization is this wave of repolarization. Now, what's interesting is if we look at local potentials are able to be different sizes. They're graded. But because the action potential constantly regenerates itself, it opens new channels as it moves along the membrane, the size of the action potential where it begins is the same as the size of the action potential where it ends. So the action potential is the same size all the way down. Actually, we would say this is non-decremental. It doesn't decrease in size as it goes down. It's either this size or not at all. That's all or none. So the action potential is always going to be at maximum because these channels open completely and the sodium flows through. It's not about how much neurotransmitter happens to come across, and that tells you how much sodium comes in. These are open, sodium comes in, then they close, and we move on. The action potential is irreversible. You can't start an action potential and stop it halfway down the axon. Because these channels are there, it's going to go all the way. And finally, it's always excitatory. Local potentials can be excitatory or inhibitory. Action potentials are always excitatory. All right, so the action potential has traveled along the membrane and it reaches the axon terminus where it encounters voltage-gated calcium channels. Those are those tiny little orange things there. When those open, calcium enters the cell because calcium is most concentrated on the outside, and that causes exocytosis of the vesicles containing neurotransmitter because we're back at a synapse and we can send that signal to the next neuron.